So today we'll be discussing the propagation of electromagnetic waves in a non-conducting medium. This propagation of electromagnetic waves in a non-conducting medium, that is an isotropic dielectric. So we start with the Maxwell's equation, the first equation. These are the four Maxwell's equations. So for a non-conducting medium, the conductivity is zero. That means the current density is zero. We label this set of equations as 1. Since the medium is isotropic, medium is isotropic, this implies that there will be no volume distribution of charge. And since there will be no volume distribution, that means the density will be 0. In these two cases, these equations will reduce to the first equation will be the same. The second one will be 0. J will be 0. These equations can be also be written as, since we know that D is equal to epsilon E, B is equal to mu H. So we can transform the fields. So this equation will give me del dot E is equal to 0. This is del dot B is equal to 0. This is del cross H is equal to epsilon del E by del T, and this is del cross E is equal to minus mu del H by del T. We label these equations as 2A, B, C, and D. Now we will consider the propagation of magnetic vector, which is H. So we will take this third equation 2C and take a curl of this equation, which will give us now using the vector identities of the double curl product. Now, using this one, del dot H will be 0. So the only term on the left side will be del square H with negative sign to this side. Now we can use this equation. Del cross E is equal to minus mu. This and this will give me substituting del cross E from this equation to this equation. Of course, mu. Now we rearrange this such that is equal to 0. It's called third equation, fourth equation. Of course, we know that the velocity of light is like this. So we can just now this was a vector, magnetic vector. We consider the propagation of electric vector E. Similarly, taking the curl of here we in the previous case we took the curl of the third to 2C equation. Now we will take the curl of the 2D, that is the fourth equation. So it will become applying the same vector identity and the same value of del dot E will be equal to 0. That's now this will be 0. So it will be minus del cross H. And the value of del cross H will be this will be we will call this equation 5. So these equations, the equation 4 and 5 are the wave equations representing the propagation of the electric and magnetic vectors. Now we assume that the wave is propagating in z direction. Since it is propagating in z direction, then del I del y will be 0 and del will be del by del z only and del square will be del 2 by del z2. Now we apply this in equation 4 and 5. So they will reduce to del 2h by del z2 psilon nu del 2h del t2 equal to 0. Now we substitute epsilon. We reduce this equal to 0. In a similar manner, this equation 5 will give me we call this set as equation 6. Now we assume that the two vectors, the electric and the magnetic vectors, which are traveling in the z direction, these now again substituting this and so what we get from this, that del by del z multiply the equation by minus ik. If it is del by del t, then multiply the equation by I omega. Now, first case, just we want to show then E and H are transverse. So del dot E is equal to 0, and in our present case this will be equal to 0. The value of del by del z is here. Two things I would like to mention, that this k is the wave vector, wave. Okay, this k is not the propagation constant, it is the wave number. K is the wave number, while this k is the unit vector along the z direction. Similarly, we take another equation, that del dot h is equal to 0, and from this equation we deduce in the similar manner this. That means we can say that if the direction of propagation is z, then from this one h is not in this direction, and E is also not in this direction. And since the dot product is 0, that means they are into the traveling in a direction perpendicular to Z. Both the vectors are traveling in directions which are perpendicular to Z. Not in the Z direction. Both direction perpendicular to Z and then are transverse. Now we see the impedance of space. So what we should show that E and H are in phase, and we will obtain the expression for the impedance. So what we have formed, let's start with the third Maxwell's equation. We will substitute the value of del cross del from this one and del by dt from this one, and simplifying, what we'll get will be and the other equation will be this is equation 7. So from this equation we can deduce that from the coordinate we know this. Sorry, that means on simplification Ax by Hy will be equal to omega mu upon wave number k. Now this k, this is equal to, this is the wave number equal to 2 pi by lambda, and in terms of frequency it will be this. Now this we convert into omega, we convert V into mu epsilon. So k is related to mu epsilon in this one way. Now we substitute it In this relation, we get omega mu epsilon. On simplification, what we get mu by epsilon to the power half. We got the equation 8. Now, the electric vector x varies as omega t minus kz and h y0 e to the power omega t minus kz. So, from this previous equation, so we solving them simultaneously, we get this one. And okay, so these are the amplitudes. What does this signify? Is there an these are properties of the medium and they will be constant. The property, the electromagnetic wave, there is no other quantity. So this Hy and Ex, they will be, both will be in the same phase. Now third is the speed of the electromagnetic wave. We need not discuss it much. We have already taken the value. In terms of the relative values, the relation will be, these are the relative values. Fourth is the refractive index of the medium. Refractive index is defined as C upon V. Substitute this value, what it will be, just interchange it, it will be mu r epsilon r. This is the refractive index. And for a non-magnetic medium, this mu r will be equal to 1. So in that case, it will be epsilon r only. Now we go to the direction of the flow of energy. This direction is defined by the Poynting vector, like you have already studied. and the value of that Poynting vector is given as E cross H. Now, on using the relation, mhm, converting this into relative values. So this is the average value. We will, this is the ninth equation, and free space, this value will be what? Now, since this is the only vector, so we can write this as E0, then this one is E0 square, and half k. This k half k epsilon 0 c e square space. So from this, we say that the direction of energy flow is the along z-axis, and this is also the axis of propagation as we have taken. So the energy flows in the direction of propagation. We conclude from this that the energy flows in the direction of propagation. That was section 4. Electrostatic energy density. Now we calculate the electrostatic energy density. The electric energy density is given as this. When we convert E into H, the electric energy density is equal to the magnetic energy density. The total energy density will be the sum of the both. Convert this and reduce to this. Both are equal, so it will be just epsilon E0 square. So now the average total energy density square. So the average power, average, this is U, this is U, this was the equation just after 9. Okay. Take this equation as 10 upon R epsilon 0 ERMS square. Now we solve this. Since half E0 square will be equal to ERMS square, now this will reduce to K under root we multiplied and divided. This is same. And see, this is 1 upon under root mu r epsilon r will be V, and this is C. Oh, sorry. C upon relative. Now we calculate the electrostatic energy density. The electric energy density is given by half epsilon E0 square. Now we substitute E0 in terms of H0. So it will be half this one. Now we reduce, cut this. It will be mu H0 square, which is magnetic energy density. So the electric energy density is equal to the magnetic energy density. The total energy density will be the sum of the electric energy density and the magnetic energy density. Since these two being equal, so we get in terms of E0 epsilon E0 square, or it can be mu H0 square, one and the same thing. The average total energy density, the average of this one, represented by U bar, is equal to epsilon into E RMS square. Now we take the ratio of the average power by the average total energy density. The average power is using equation 10. So we substitute the expression for the average power from equation 10 and the total average total energy density from this equation. On simplification, here is half E0 is 0 square is equal to E RMS square, and we cut this, we get this expression where C is the velocity of light, and upon simplification we get this, which is this ratio is the velocity of light. Thus average power is equal to unit vector K into the average total density into velocity of light. So what does this signify? That the energy is transmitted with velocity equal to phase velocity of the wave, and direction is the direction of propagation. In other words, along in the direction of propagation. So this was total electrostatic energy density. So we end our topic here, and for any doubts, you can leave a message in the comment box or write to me, and we will be discussing the propagation in the conducting medium in the next lecture. And I request you all to subscribe to the channel and like the video. That's all for today. So we'll be back with another lecture shortly. That will be propagation of electromagnetic waves in a conducting medium. Thank you.